Hello, for today's video lecture, we're going to be talking about the parallel axis theorem. So, as we saw in the previous sections, the area and mass moments of inertia we calculate will depend on the origin point we're setting at the start. So if we choose a different origin point, we will get a different moment of inertia value in the end. We can illustrate this by trying to rotate a broomstick around different positions. So if you have a broomstick around, you can try this. So if you have the broomstick, it's going to be easier to rotate about the center point. So kind of grab the center point and kind of rotate back and forth. And that's because it's got a lower mass moment of inertia. If we instead look at the end, so grab it at the end and kind of rotate at that end point, it's going to be harder to rotate because it's got a higher mass moment of inertia. These are both the same shape. We haven't altered the shape. We've just altered the point we are rotating about. And so with this, we are changing the mass moment of inertia in this case. So because we could potentially choose any point to rotate a body about, there are potentially an infinite number of moment of inertia values. This is different than we had with the centroid calculations we had earlier in this chapter. There is one centroid or one center of mass. There are infinite moments of inertia in any shape. So even though there's an infinite number of values, they're going to go up and down in a predictable fashion. And we can use the moment of inertia at one point to find the moment of inertia at another point using something called the parallel axis theorem. So the parallel axis theorem states that the moment of inertia is going to be lowest at the centroid or center of mass value. So lowest at the centroid for an area moment of inertia, lowest at the center of mass for a mass moment of inertia. So if we were to take the moment of inertia about another parallel axis that is distance r away from the original axis, the moment of inertia value would increase by a quantity of area or mass times that distance squared, so that r value squared. And so in equation form, what this looks like is IXP would equal IXC plus AR squared, or IXXP is equal to IXXC plus MR squared. So the top one is for area moments of inertia, and it's stating that the area moment of inertia about any point P is going to be equal to the area moment about the centroid plus the area times that distance between the axes squared. So whatever x-axis I'm using for this part and whatever x-axis I'm using for this part, distance between those two is my r term. Same thing down here, the mass moment of inertia about any point P is going to be equal to the mass moment about the centroid plus the mass times that distance between axes squared. So let's look at the r term. The r term is the big thing in this. The area for area moments of inertia, it's important to identify how far the axis has moved. It's not how far the origin point has moved necessarily, but how far the axis has moved. So say we've got some rectangle up here. I've got the centroid, and say I've calculated my IX and IY values around that center point, and I want to figure out what the moment of inertia would be about some point down here. So if I want to adjust IX values, I'm going to look at how far the x-axis moves. So in this case, the distance the x-axis moves is going to be a vertical distance. It's a little bit confusing there. So Ix, your r value is going to be a vertical distance. If I'm looking at how far or how much to adjust the Iy value, that's going to be a horizontal distance. So the y-axis is moving from here over to here. And then if I have z-axis, so even though this is 2D, this would be the polar moment of inertia, that is going to be a diagonal because the z-axis is pointing out of the page, and so it's pointing out of the page down here. The distance between those two kind of vectors or directions pointing out of the page is going to be the diagonal value there. So you want to make sure you're looking at how far the axis moves, not necessarily how far the origin point moves for all of these. And also, because we're squaring the term, it's AR squared or MR squared, the direction is important. So don't worry about positive or negative, left or right. You just want to figure out the distance between those two axes and generally leave it as positive. For mass moments of inertia, again, same thing. We want to determine how far the axis is moving. So if I have Ix about the center point, and I want to figure out what is the moment of inertia about the endpoint, my r value is simply going to be the distance between those two axes. One thing I'm going to point out with this is also applicable to the area moments of inertia is this doesn't work if we are changing the direction of the axis of rotation. So if I wanted to adjust from the center point over here to this moment of inertia axis about over here, that's not going to work. And the reason is this is the parallel axis theorem, as we saw here. We can only move the axis if we are keeping it parallel with the original axis. So if I want to find something like this, I need to start with an axis, have a moment of inertia about the axis direction that's the same as this, and I'm just moving it up, down, left, or right from there. All right, so why do we care about this? So it can be useful in certain cases. If I have a moment of inertia about one value and I want to find another, I can use it there. But more often, this is going to be related to the centroid calculation, or this is going to be related to the method of composite parts. So just as we did for centroid calculations, we can use something also called the method of composite parts to calculate area and mass moments of inertia using moment of inertia tables for common shapes. An important part of this whole process is going to be using the parallel axis theorem to adjust the moments of inertia so that they're all taken about a common point before we can add those values together. Because if moments of inertia are taken all about different points, we cannot add them together and get a valid result out of the whole process. So more about that will be talked about in the next sections. Thank you for watching, and I hope to see you again.